In this video, we're going to go over a few different reactions, identifying which mechanisms we are going to work according to in each one, and then drawing out those mechanisms to predict the outcome of the reaction. So, our first one is going to be a butane with a chloro group on it being reacted with sodium iodide in plain old water. So let's take a look at our flow chart. So if I look at my flow chart, first thing, this is a primary substrate. So I've got the primary right here. Is it a strong base or nucleophile? Well, I'm going to be working with iodide. And iodide is not a strong base. It is very stable. However, in a protic solution, it does become a strong nucleophile. So I've got a stronger nucleophile than it is a base. It's a better nucleophile than it is a base. So I'm going to be following just the Sn2 reaction. Convenient. So I'm going to be running the Sn2 mechanism for this reaction. Let's set it up. So now that we have our substrate and our nucleophile all set to go here, all we need to do is draw arrows showing the attack. Next, we just draw out our final product. And these are our products. So then we can just write those in up here with our reaction. And that's the whole thing. It wasn't too bad. Let's try another one. In this reaction, we have a tertiary substrate with an iodo group being reacted in a solvent of methanol. So it's going to be reacting with the methanol, and it's going to be inside of concentrated methanol. So this is not going to be a solution with methanol and water or anything else. Methanol is the solvent. It is also the nucleophile. So we'll have to look at that. With that in mind, we have a tertiary substrate. So following our flow chart, we go to our 3, and then is this a strong base? Well, methanol is not a strong base. The OH group could act as a base, but it's not a strong one. So we're going to have a no here, a solid no. So we're going to get E1 and Sn1 products. Let's start by drawing out our Sn1 mechanism. Our first step of Sn1, we are going to be losing our iodo group. That's going to be our leaving group. In our second step, our methanol is going to attack our carbocation. And so one of our electron pairs here is going to be attacking that. This is why we need a weak base, because methanol normally would not be attacking using one of its electron pairs, but in this case it does. So now we have our Sn1 product. We could report it as this, or if we know what's going on here, we would see that this hydrogen isn't really going to be that stable on this oxygen. It's not going to be an alcohol. It's going to be an ether. And so this hydrogen will want to vacate the premises. And so this bond will actually go onto the oxygen and will lose that hydrogen. And so we have our Sn1 products. Now we need to account for our E1 products. So now that we've got our substrate drawn out, we just need to do our first step of the E1 reaction where the iodo group leaves. In our next step, we have the methanol attacking this hydrogen, taking it away, this hydrogen giving its bond over to this carbon and this carbon to form a double bond here. But to find stability, this methanol is probably going to take one more step. You would not need to report this on your answers. You could just report it this way. I'm going to take it one more step and say that this hydrogen is going to leave, finding its own way. And in doing that, I'm left with an H plus and an I minus, and this just makes it easier to report my actual products at the end of this, because I end with this ether along with this alkene, some hydroiodic acid, and I'm still going to have my solution of methanol. So there we go. Here's our next reaction. We have a secondary substituted carbon attached to a chloro group that is going to react with sodium hydroxide. Hydroxide will be the nucleophile in a solution of H2O. So let's go to our flowchart and see about that. So this reaction is using a secondary substitution on our substrate. So we've got 2 degree here. Is it a protic solvent? Yes, water is going to have hydrogen binding. So yes, and then is it a strong base? Absolutely, this is a strong base. This is hydroxide, one of the strongest bases. So yes, we're going to have an E2 reaction, and only an E2 reaction. Fancy that. Now, looking at this, normally we would say, I could have an Sn1, I could have an E1, those could still happen. According to this whole situation, that's still a possible reaction. And of course it is still a possible reaction. Just like technically speaking, the Sn2 would be a possible reaction here. This OH could easily attack this substrate. But because this is in water, this gets surrounded, and this hydroxide pulling away this hydrogen is going to happen so much quicker than the Sn1 or the E1 could. So even though I could have this group leaving first and then resulting in me having an Sn1 reaction, that's going to take longer than this hydroxide to just kick off this hydrogen. So it is going to be a lot faster to go through the E2. And because of that, most of my products will be E2, to the point where it's not even worth mentioning what I would have through the Sn1 and the E1. So we should have enough of an understanding of how these mechanisms are occurring to identify where could they work, but that they would work too slowly in those contexts. So my first step here is this whole thing is going to happen in one step. My hydroxide is going to attack the hydrogen. The bond of the hydrogen is going to go towards these 2 carbons, and this bond is going to be given to this chlorine. So we get 3 arrows, each showing the movement of our electrons. And then that all occurs in one step, and we get an alkene, water, and a chloride anion. So water is my solvent, so it's just going to stay there. I'm not going to include it in my products, but I am going to have an alkene and some sodium chloride. So there we go. That's the whole thing. In this reaction, I have a pentane attached to a bromo group, which is being reacted with sodium acetate in a solvent of DCM. DCM is dichloromethane. It is an aprotic solvent. It is very polar, but it has no hydrogen binding whatsoever. So let's take a look at our flowchart and determine which reactions we're going to be having here. So looking at this, I'm going to have a secondary substituted substrate. Am I protic? I am not. DCM is an aprotic solvent. So no. Is this a strong base or a strong nucleophile? Well, acetate is going to be both. It's going to be both a strong base and a strong nucleophile, so we're going to get both the Sn2 and the E2 reactions. Got the start of my Sn2 reaction set up here. My acetate is going to be attacking the carbon that is attached to the bromine. That carbon is going to give up its bond with that bromine, and that bromine is going to be a bromide anion floating away. Next, I can write out my E2 mechanism. In my E2 mechanism, the first thing that's going to happen is the acetate is going to attack the hydrogen. The hydrogen will give up its bond with the carbon it's attached to. And then the carbon that that carbon is attached to, so my beta carbon here, is going to give up its bond with the bromine. The bromine is a stable leaving group, so the bromine is more than happy to take on this extra pair of electrons. And so because of this situation, I actually end up with a few different products. First off, I have my ester right here that's going to be attached to this acetate ion. Next, I'm going to have my alkene here. It's just going to be a pentene. Following that, I actually end up with some acetic acid. This is a carboxylic acid right here. And finally, the bromide anion takes the place of the acetate anion in bonding with the sodium. And so because of my different reaction mechanisms, I actually end up with 4 distinct products in this reaction. For our next reaction, we have a primary substrate attached to a bromo-functional group that is going to be reacting with the nucleophile azanide, which is bonded to a sodium. All of this is going to take place in water. Looking at my flow chart, this is going to be a primary substituted substrate. And is it a strong base or a nucleophile? Well, the azanide is both a strong base and a strong nucleophile. As we go across the top of the periodic table, our nucleophilicity is going to follow basicity. And so once again, we're going to have both the Sn2 and the E2 reaction mechanisms. So let's draw those both out. In our Sn2 reaction, our azanide is going to be attacking this carbon to get rid of this bromine. So we attack there, release there. So the first of our products is an amino group. Here's our setup for the E2 reaction, where it works a little differently. First, I'm going to have my nitrogen attacking this hydrogen, pulling it away. This hydrogen is going to give it its bond with that carbon. That electron pair stays with the carbon. And then this bond gets broken with the bromine so that this carbon can attach to this carbon. So the bromine takes away that bond. It takes that electron pair away. And so the products that we get from the E2 mechanism are just a simple ethene, or propene, a propene, along with an ammonia. So this reaction would actually start to smell pretty strongly of ammonia. There we go, 4 products. Our next reaction, we have an amine attached to a butane. And this is going to react with methanol with an acid catalyst. So methanol is going to be both our nucleophile and our solvent. And we're going to use H2SO4, some sulfuric acid, to catalyze this reaction. That should make sense considering NH2 is a very strong base, so it's a terrible leaving group. It does not want to leave. But using this acid catalyzation will allow us to get this to get the hell off of our substrate. So let's take a look at our flow chart to figure out which reaction we are going to be producing. So once again here, we have a secondary substrate. Our solution is going to be protic. Methanol is a protic solvent. So yes, is this a strong base? Methanol is not a strong base. So no. So we're going to have E1 and Sn1. So before anything can happen with our mechanisms, we first need to look at our acidification of our amine. This is going to happen quite quickly. This is what's going to allow this to be a good leaving group. Our nitrogen here is going to use its extra electron pair to attack this positive hydrogen. So once it does that, once that occurs, we get a ammonia as a functional group, which is it's a fantastic leaving group. It's a horrible base. It is not very good at holding on to anything, and it's going to be it would much rather hold on to these hydrogens than to this carbon. So that's a great leaving group, and we can start our Sn1 and E1 mechanisms. Let's start with the Sn1 up here. First thing that happens in the Sn1 reaction is this amine group, really ammonia, is going to leave. So it's going to take this bond and it's going to go. Now, the normally weak base methanol is going to be very attracted to this carbocation. And so it's going to swing and attach. And finally, it's not exactly the most stable thing in the world with that hydrogen sitting there, so that hydrogen is going to leave. Likely, it'll get taken up by this ammonia to make the ammonium ion. So there are our Sn1 products. Let's take a look at the E1 products. So here's our setup for the E1 mechanism. The first thing that's going to happen is our leaving group, just like in the Sn1, is going to leave. Next, this methanol is going to be attracted to that hydrogen, so it is going to take it. Finally, since ammonia is a weak base, it's likely to take the hydrogen from the methanol, which, in all stability speaking, it doesn't really want. So, after all of that, what we really end up with is this ether, some ammonium, our methanol that we originally used, a butene, and more ammonium. Now, the ammonium is able to take the place of that initial hydrogen that the H2SO4 lost, and so we end up with some ammonium bisulfate as a final product. Let's write in all of our final products and be done. So, with all of that practice under our belts, we should be a lot better at predicting the outcome of substitution and elimination reactions. That was a lot of work, but we should be very well prepared now. We should have a pretty good understanding of what is happening on the molecular level. We should be able to describe what's happening and really explain, using cause and effect language, how these reactions actually occur. What is the actual mechanism that these reactions are occurring by?